Anybody want to ask any question, any doubt, anything, whatever we have discussed so far? Okay, so then let me start. So last class we were discussing this no, the Euler-Bernoulli beam finite element. So we will continue with that. Euler-Bernoulli beam finite element. So that is what we were discussing in the last class. So we had discussed, of course, the governing differential equation, and as far as the weak for weighted residual statement weak form and the integral functional interpretation of the various terms of here, total potential energy functional or integral functional are concerned, that was discussed in the earlier class. So since we said that highest order derivative in the integral functional is second derivative of v, and v and dv by dx are the primary variables. So minimum, of course, we should have two nodes in the element, and the primary variables, so that is v and dv by dx, should be degrees of freedom. So we had v1 at first node and the rotation, so that rotation we said dv by dx at node 1, and this be denoted as theta 1 e. And similarly we had v2 e and dv by dx. So yeah, I used capital X, so let me just do that. So d capital X. Of course, the derivatives are same whether you take with respect to global x coordinate and local x coordinate, they are same. So this is equal to theta 2 e. So these were the degrees of freedom, two at each node. Those are basically, these are nothing but the primary variables, and we are having no, we are keeping these primary variables as degrees of freedom, so that during the assembly we can impose the continuity of these primary variables. So then these are the four degrees of freedom for the element as a whole. So we will have to assume the polynomial which has got four terms in the approximate solution, and that is v0 v equal to a0 plus a1x plus a2x square plus a3x cube. And of course, from the continuity requirement, we need only up to x square, but from the because to satisfy the inter-element compatibility, we need 2 degrees of freedom at each node, v and dv by dx, and total for the element 4. So we should have four terms in the approximate solution, and that is how we led to the cubic polynomial. So that we had done, and then I had said no, that whatever approximate solution we had got, so we substitute that in the integral functional or total potential energy functional I. So we had got this I equal to half of integration 0 to L. So this we actually did in the last class. So we had EI, and then D transpose into B transpose into B into DE dx. So this the strain energy part, and then the potential energy of the externally applied load. So that was d transpose into h transpose into q dx, and then we had this internal force. So that is d transpose, and the internal forces are minus s1e minus m1e and s2e and m2e. So this is what we had got earlier, and so basically, as you so we denote this vector by the internal load vector. So this is f internal E, And so now, as I said, because no, this b no, here if you see, b is a function of x, but d is the nodal values of v and dv by dx, so that is independent of x. So this can be taken common on the left hand side, and this term can be taken common on the right hand side. So if you do that, so we can write this I is equal to half, and then this d transpose taken common on the left hand side, and then we have integral 0 to L, and then ei and b transpose into b dx. So this matrix is there, and then this d we are taking on the right hand side, this d, and that the integral is already inside now. And similarly, now in this term, d transpose can be taken out of the integration sign, so we'll have d transpose and then integral 0 to L h transpose into q dx. And of course the last term is anyway is d transpose into, this is we are calling as f internal, internal load vector. So this is what we will have. And out of this, as you know already by now, we have defined the quantities. So this we call as element level stiffness matrix Ke, and what we have over here, this term we call as the external load vector f external for the element. So now with these nomenclatures, you can actually say that I will be half of d transpose into Ke. K is the element level stiffness matrix, minus we will have this d transpose into f external for the element, and minus we will have this minus de transpose into f internal for the element. So there is a minus sign over here. So this is what your I is, and we know that for equilibrium, or the solution of the original differential equation, the delta I should be equal to 0. So for because that is how we have got to this, from the differential equation to the better residual statement to the weak form, and from there delta I equal to 0. So that is same thing we are invoking here. So for equilibrium, because no, the whole beam is in equilibrium, so each and every part, and therefore each and every element has to be in equilibrium. So for equilibrium of the element, delta I should be equal to 0. So if you write the expression for delta I, you would see that delta I will be equal to, we have already discussed no the in the when we talked about the truss element. So we will have two terms when we take the variation of this. So variation of this into this whole term, then second term would be this into this plus variation of this, and those can be combined together. So finally we get delta de transpose into ke into de minus delta d transpose into f external for the element, and minus delta d transpose into f internal for the element, and this would be equal to 0. So now we know that this has to be delta I should be equal to 0 for arbitrary delta d. Arbitrary means it can take any values, of course infinitesimally small values, and kinematically admissible, but then the 4 degrees of freedom, d involves v1e theta 1e v2e theta 2e. So we could have any arbitrary variation, we can have variation in any one or in all, but for all those cases this delta I should be equal to 0. So for that we write that for arbitrary, for one particular combination without the KED equal to f external plus internal, this could be 0. But if it is arbitrary, then for arbitrary delta DE, this delta I equal to 0 gives basically this element level governing equation, which is KE into DE is equal to f external for the element plus f internal. So this is the equation you get, and this is the same. So if you look at the equation is actually the same, the element level governing equation. So far we know that only thing is the sizes of the matrices and the degrees of freedom are changing. So k in this case would be 4 by 4. How? That is integral 0 to L, and then we have EI and B transpose into B dx. So here if you see B is 1 by 4, B transpose would be 4 by 1. So their multiplication is going to give a 4 by 4 matrix, and therefore K is a 4 by 4 matrix for the this two noded beam element, Euler-Bernoulli beam finite element. And the F external is nothing but that is a 4 by, it is going to be 4 by 1 vector, which is integral 0 to L, and H transpose into Q dx, and H is 1 by 4, its transpose is 4 by 1, and that is how F external is coming as 4 by 1 vector. And as you know, the F internal is basically the shear force and bending moment at the left and the right end of the element. So minus S1E minus M1E, S2E, and M2E. So this is the internal load vector. So this is basically becomes the element level governing equation. Now for the applications you have to integrate and get Ke and F external, and then assemble, impose the boundary condition and solve the problem. So those steps are basically same. So let us look at the specific forms of this Ke and F external if Ei and Q are constant within the element. So let Ei, although they could be any function, you can account for, let's say half of the element has got some value of E into I, and half of the element another value of Ei. Then you can split the integral 0 to L by 2 and L by 2L, and for L by 2 you have one value of Ei, and for L by 2 to L another value of Ei, or it could be some function of x. So then you put that function, and then you have to carry out the integration, integral 0 to L Ei B transpose B dx. So as a specific case, I am assuming that let Ei and Q be constant along length of the element, length of the element. So in that case, if you look at the Ke, so Ke is going to be, because Ei is constant within the element, can be taken out of the integration. So I can write Ei and then integral 0 to L B transpose, and B transpose we have already seen, it is d2h1 by dx square, d2h2 by dx square, d2h3 by dx square, and d2h4 by dx square. So this is B transpose, and B is of course again same thing, d2h1 by dx square, d2h2 by dx square, d2h3 by dx square, and d2h4 by dx square dx. And we already know this is 4 by 1 and this is 1 by 4. So the multiplication is a 4 by 4 matrix. And if you multiply this, so you will get this as Ei integral 0 to L. And basically when you write in this manner, that means the integration has to be performed for each element of the matrix. So if you multiply, this row with this column, this column, this column, this column, what you will get is d2h1 by dx square whole square, and then d2h1 by dx square into d2h2 by dx square, and d2h1 by dx square into d2h3 by dx square, and d2h1 by dx square into d2h4 by dx square. So like that, no, you do the multiplication. So then you take the second row d2h2 by dx square and multiply with the first column, second column, third column. So you'll get the second row. So like that, no, you can multiply and get all the four rows. I am not writing that, it's straightforward, you can actually write that. So now if you integrate each term, so for that we need the second derivatives of the shape functions. And the second derivatives, we have already defined the Harmonic interpolation functions for this Euler-Bernoulli beam element. So H1 was 1 minus 3 x square upon L square plus 2 x cube by L cube. So this was H1, its first derivative dH1 by dx would be equal to minus 6x by L square plus 6x square by L cube. So this is the first derivative of H1, and then if you differentiate it again, so d2 H1 by dx square, now you are differentiating this again, so minus 6 by L square and plus 12x by L cube. So this is the second derivative. So similarly you have H2 H3 and H4. So if you differentiate twice, you can get the other derivative. So similarly you can see that d2 h2 by dx square will be equal to minus 4 upon L plus 6x upon L square, and d2 h3 by dx square will be 6 by L square minus 12x by L cube, and d2 h4 by dx square comes out as minus 2 upon L plus 6x upon L square. So these are the second derivatives. So now you put all the values over here now in this matrix and then integrate. So of course that some algebra and the integration you have to do. So finally after integration, so I am writing the end result. So finally after integration, if you carry out the integration, so you will have ke is equal to I am taking this ei by L cube common, so this comes out as common, and then the matrix comes as 12 6L minus 12 6L, and then you have 6L 4L square. So these are the integrations, minus 6L to L square, and then we have minus 12 6L 12, and again minus 6L, and then we have 6L 2L square minus 6L 4L square. So this comes out as your element level stiffness matrix for the Euler-Bernoulli beam finite element. So one thing you would notice always, like if you remember, in case of a two-noded truss element, we had diagonal elements of the stiffness matrix positive, off diagonal elements were negative, and three noded truss element, of course, we again had diagonal elements positive, and some of the diagonal elements were positive and negative. So same observation is here. So you would see that all the diagonal elements are positive. Here element means, when I am referring to the elements of the matrix, means basically these are also referred to as elements of a matrix. So that is what I am referring over here. So you can say that here all the diagonal elements, or you can also say all the diagonal terms. So to differentiate between finite element and this, so you can say all the diagonal terms are positive, but the off diagonal terms are positive and negative. So if you look at the off diagonal terms, so the off diagonal terms are, some of them are positive and some of them are negative. So that is what observation you make over here. And then if you look at the external load vector, so because we are saying that small q is constant within the element, so can be taken out of the integral. But keep in mind, no, if q is or ei is given as a function of x, so you have to keep it inside, multiply with the other matrices, and then you have to integrate integrate each term. So no, let's say ei is was a function of x, so this element then would have come from integration of integral 0 to L ei, which is a function of x, into d2 h1 by dx square whole square dx. So you'll have to integrate that term, multiply all the three terms then, and then integrate. So that is what you have to do. So similarly here, now if q is a function of x, then you have to multiply q and h1 and then integrate the resulting thing. So but for the timing, I am saying that that is constant, so you get this as dx. And I leave it to you to verify that no, the result, no, if you integrate h1 it will give you L by 2. If you integrate h2 from 0 to L, it will give you L square by 12. If you integrate h3 it will give you L by 2, and if you integrate h4 it will give you minus L square by 12. So therefore this load vector would be q, and then first integral is L by 2, L square by 2, L by 2, and minus L square by 12. So no, of course, no, the way we derive the load vector like this through the use of shape functions. So as you already know, we have earlier used this terminology. This is known as consistent load vector. Consistent load vector, because now we are deriving the load vector based on the shape function. So it is consistent with the shape function or interpolation of the known displacement, that is v. So another possibility is that you can also use lumped load vector. But I am giving you, I know telling you this concept, but we are going to use consistent load vector only. That is more accurate. So for the lumped load vector, what you can do is we are already taking the load q constant within each element. So the total load would be, transverse load would be small q into L, and then what you can divide is you can equally divide that between the first and second node. So it would go with the load would go with the displacement. So first would become ql by 2, and we are not taking any moment. So because second term of the load vector is corresponding to the degree of freedom theta 1, which is a rotation, so this would be actually moment. So we are not taking in moment, but the total load is divided between the two nodes. So this could be one possible lumped load vector. So but we are going to basically use this particular load vector. So once we have this, so then yeah, you can basically use this now the element to solve problems. So let's look at the applications of this Euler-Bernoulli beam element for solving the simpler problems. Of course, you can solve more complex problems like the entire, let's say the network of rings and stiffeners in a submarine. So all the basically stiffeners and rings would be subjected to transverse load, and you have to discretize the whole thing into a certain number of elements, and then assemble and impose the boundary condition and solve the problem. So that is a more complex problem. But to understand the application, because when we understand the application to simpler problems, it can be extended to complex problems. Of course, for very complex problems, you would not do it manually, but you will have to either do through a code written in MATLAB, or you use the commercial softwares like ANSYS, Abacus, and so on. So let's look at the some applications, simple applications. So first I am taking a beam fixed at both the ends and subjected to uniformly distributed load. So let us take beam fixed at fixed beam fixed at both the ends. So that is what I am doing is taking this beam, and it is fixed at both the ends. So I'm showing this as a fixed beam. And now as far as the load is concerned, so there is a distributed load, although there can be no distributed load, only concentrated load may be there. So all those possibilities are there. So this is the distributed load q, and its flexural rigidity, that is ei, a product of Young's modulus and second moment of area. Ei, we call it as flexural rigidity. So I'm assuming that it is constant within the each element. Now one thing is, if you now how many elements to use to discretize this. Now you have to divide this whole beam into a number of elements. Now number of element could be just one element, but if you take one element, then because it is fixed, so this end v and theta, v and dv by dx are going to be 0. This end also v and dv by dx would be 0. So if all of that means, if we are discretizing this into only one element, then all the 4 degrees of freedom would be 0. So it will give you a zero displacement everywhere. So that would be a trivial solution. So for this, at least you have to discretize this into two elements, two noded Euler-Bernoulli beam finite elements. Why Euler-Bernoulli beam finite element? Because the loading is transverse. If the loading was in the along the length of the this rod, then you would have discretized this using truss element, which we have discussed earlier. So now the load is transverse, so we discretize this using beam element and two beam elements. So it will have four nodes. So let us say this is global node number 1, this is global node number 2, this is global node number 3. The element numbers are, this is element number 1 and this is element number 2. So inside the circle I am showing the element numbers, and without circles are the global node numbers. And length, let us say each element, let us take small l, we are taking both the elements identical, so the length is small l. So you would see that if the total length of the element is L, so yeah, capital L, then this will be L, or you can say that small l is going to be L by 2. So I have already mentioned to you that one element solution will give you, so if you just discretize this using only one two noded Euler-Bernoulli beam element, so one element solution will ultimately give you V equal to 0. So we are not able to know, that is we have to at least discretize this into two elements. And of course ultimately the number of elements, so that 2 or 4 or 8 elements will depend on the convergence study. So you have to initially start with, let's say, two element and solve the problem and get them, say, maximum deflection and maximum stress, and then discretize using four elements and then again get the maximum deflection and maximum stress. And if the two solutions are close, then you say that two element solution is accurate enough. And if two and four element solutions are different, then you go for more number of elements, say 8 elements, and then again compare the results of 4 and 8 elements, and if they match, then you can say 4 element solution is a converged solution. So that convergence study has to be done always to ensure that we are using sufficient number of elements. But here, to demonstrate the solution steps, I'm just taking two elements. So I already told you that at least, because one element solution gives you V equal to 0, so at least two elements are required. And that is what I have done. So discretize this using two elements. So now once we have discretized this using two elements, so now the next thing is the assembly. Because element level governing equations we have already developed. So now if you look at without any boundary condition, so assembly we don't worry about the boundary condition. After we assemble the equation, we can impose any possible boundary condition. It could be fixed at both the ends, it could be simply supported, it could be fixed at one end, free at the other end, or it could be fixed at one end, simply supported at the other end. So all those boundary conditions can actually be imposed, so you should be able to do these solutions for different boundary conditions. But now before that, let's say there are total three nodes, node 1, 2 and 3, and at each node we have 2 degrees of freedom, v and theta, that is theta is nothing but dv by dx. So we will have total 6 degrees of freedom. So if you look at the stiffness matrix, the stiffness matrix is going to be of size 6 by 6. So that means when you're looking at the stiffness matrix, it is going to be of size 6 by 6. So this will be the stiffness matrix, and then the vector of degrees of freedom, and then you have on the right hand side the vector of external force and the vector of internal force. So this is what you will have, and this global equations will have 6 rows and 6 columns in the stiffness matrix. So say 1, 2, 3, 4, 5 and 6, and similarly we will have 6 rows. So 1 and 2, 3, 4, 5 and 6. So yeah, these are no rows and columns. So now coming to the assembly, because we are taking both the elements identical, So ei by l cube is same for both the elements, so that can be taken common. And although there is no change in the procedure, if suppose one element has got flexural rigidity as ei1 and another has got ei2, so then you will have to keep that inside, and no, you can assemble, of course, exactly in the same manner. And then in that case you would not be able to take ei by l cube common, but you'll have to keep it inside. And even the lengths of the elements could be different, but for the timing, because each element has got same value of ei and the length of the element is same, so I can take this ei by l cube as common. So that's what I'm doing. Now we are taking the contribution of first element to the global stiffness matrix. Now the first element is stiffness matrix. We have seen it is of size 4 by 4, and it is consisting of its starting node is global node number 1 and the in node is global node number 2. So it's first four rows and columns will go to the first four rows and columns of the global stiffness matrix. So that means, because that's how the node numbering is, although you should be able to do the assembly with any arbitrary node numbering. So this is a 4 by 4 element level stiffness matrix, and it will go into first four rows and columns of the global system. So the first row will go to the first row and first four columns. So we will have here 12. And as I already said, if ei by l cube was not common, so then you will have to take that inside. So it would be like here you will have to take 12 ei by l cube and so on. So this would be 6l and then minus 12 and again 6l. Then the second row, if you look at, that is 6l, 4l square minus 6l and 2l square. Then the third row, if you look at, minus 12, 6l, and then you have 12, and then you have minus 6l, and then you have the fourth row. Go to the fourth row, 6l, 2l square, minus 6l, and 4l square. So this is where the contribution of actually the first element goes, and then the contribution of second element. So the second element is, I wanted to change color. I think it is, I wanted to change this color. Okay, I'll continue. So now if you see the second element, no, that is this particular element. So the second element is defined between global node number 2 and 3. So the degrees of freedom are, no, first two degrees of freedom v1 and theta 1 at global node 1, and then we have v2 and theta 2 at node 2 and v3 and theta 3 at node 3. So basically, if you see, the element 2 is defined in terms of uh, third, fourth, fifth, and sixth degrees of freedom. That is, no, v is of the second node, which is a global third degree of freedom, theta of second node, which is a global fourth degree of freedom, then v of node 3, which is global fifth degree of freedom, and theta, which is global sixth degree of freedom. So the stiffness matrix of second element will go to third, fourth, fifth, sixth rows and columns. So because the two elements are identical, so the stiffness matrix of the second element is also same. But the first row and first column of the second element will go to third row and third column of the global system. So it would be going over here. So we will add here. So this will become plus 12, and then here we will have plus 6l, and then we will have again here we have minus 12, and then we have 6l. So no, I'm sorry, I wrote it at a wrong place. So this is here my third row, so minus 12 and 6l. So you see, these are the contribution from the second element. So first row of the second element is going to third row of the global system, and columns are third, fourth, fifth, and sixth. Then the second row will go to the fourth row of the global system, and columns would be 3, 4, 5, and 6. So we'll have plus 6L over here, and then plus 4L square, and then we have minus 6L and 2L square. And then no, the third row of the second element will go to the fifth row. So we will have minus 12, 6L, 12, and minus 6L. And then the last row of the second element will go to the sixth row of the global system, and starting with the third column, so 6L, 2L square, minus 6L, and 4L square. And wherever we don't have anything, those elements you put as 0. So this will be 0, 0, and fifth row first and second column 0, sixth row first and second column should be 0. So this is the global assembled stiffness matrix. The degrees of freedom in terms of global, I know you keep in mind that in there we are already saying that no, the at node 2 you have degrees of freedom from the first element, you have degrees of freedom from the second element, so you are saying that they are the same. So we have v1, and then we have theta 1, then for the second node we have v2 and theta 2, and then for the third node we have v3 and theta 3. So these are the global degrees of freedom. V1 is the transverse displacement, and theta is the dv by dx, which is slope. Now coming to the load vector, so the first element load vector will go to the, because first element is defined between global nodes 1 and 2, so its contributions will go to the first four rows. So the first element is ql, and then ql square by 12, and then ql, and minus ql square by 12. So this is the contribution of the first element. Then the second element contribution will go to the third, fourth, fifth, and sixth rows. So this will be plus QL, and here we will have plus QL square by 12, and then QL by 2, and again minus QL square by 12. So this is the contribution of second element. So these are the contribution from the first element, and these are the contribution from the second element. So these are the contribution from the second element. Now the internal load vector, so the first element is, we are putting the superscript as the element numbers. So we have minus s1, we have minus m11, and then we have the s21, and then we have m21. So this is the contribution from the first element in the internal load vector. Then the second element we will have minus here s12, minus we will have m12, and then we will have basically s22 and m22. So this is the contribution of the both element and 1 and 2 in the global system. For the internal loads we are using superscript as the element number. So this we call as whatever we call it as global system equation. So this is the the equilibrium equation for the system as a whole, global system equation. And let us give it as equation number. So let us say that this is equation number 1. So once we have done this assembly, then next thing comes is the imposition of the boundary condition and solution of the equations. So now if you see, as far as this equation number 1 is concerned, it is valid for any boundary condition. I just said it could be either both ends fixed, both ends simply supported, one end fixed, other end is free, one end is fixed, other end is simply supported. So any kind of boundary conditions can be imposed with this assembled global system equation. So now for the given problem which I started with, so for that if you consider no, look at the boundary conditions. So the boundary conditions are, now for the problem we have started with, that is fixed beam. So the first node, because it is fixed, so no, you have to understand that fixed means it is not allowed to move in this direction. So v is 0 there, and it is also not, because it is fixed, no, this kind of a support, so it is anchored, so it is not allowed to rotate. So theta will also be 0. So v and theta are 0. Similarly, same thing at node number 3, global node number 3. So that means we will have v1 is equal to 0 and theta 1 equal to 0. And the second is for the global node number 3, we will have v3 equal to 0 and theta 3 equal to 0. That is deflection is 0, slope is 0. It's a fixed beam. Now the third set of boundary condition is, so is no, that means now we have got this v10 theta 10, this v30 theta 30. So the unknowns are now this v2 and theta 2. The additional unknowns are now, this is an unknown, this is an unknown, s22 is an unknown, m22 is an unknown. But how do we get know this s21 minus s12, m21 minus m12? So that is what we need to look at. And similar to what we did earlier, so for the third, finding out the values of these in terms of the externally applied loads at no, yeah, no particular node, we need to look at the free body diagram of global node 2. So third set of boundary conditions will come from the free body diagram of. See, you don't have to draw this free body diagram always, but to explain you, I am showing this. No, once you understand the concept, you would no, we will you would be able to easily identify that this S21 minus S12 would be equal to transverse force at node number 2, externally applied transverse force at node number 2, positive along the positive y direction, and similarly M21 minus M12 would be equal to externally applied moment at node number 2, positive along the about positive z axis. So you can directly do that, but how we get to that is, that is what I am demonstrating through the free body diagram of global node number 2. So VFBD means free body diagram of global node 2. So if you want to draw the free body diagram of this node, so this is the node over here, this is the node number 2 we are talking about. And let us say that there is externally applied force, concentrated force P. For the given problem, this is actually P0. And let us say there is also externally applied moment M. So these are the externally applied forces and moments. So let me write it more. So this is M over here. So now if you look at no, because we are drawing the free body diagram of the uh, the node, so we will get the forces from the element. So if you look at the element on the left of this node, so you have no, basically no, this element. So if you look at the free body diagram of the element itself, so this is what you have, and left side you have S11, and this is a bending moment. You have M11, and the coordinate directions are, no, this is x and this is your y direction. Z is coming out of the screen, and the right side of this element you will have, no, here S21, and you will have this M21. So now opposite of these, no, this force and this moment is going to act on node number 2. So we will have this, which is S21, and we will have opposite of this, so moment would be like this, and this will be M21. And similarly, if you look at the element on the right hand side, although no, when you are drawing the free body diagram of node 2, you need not draw the FBDs of these elements, but for your understanding I am drawing that. So now you have, no, this q over here, q is there, and then for the element as whole you will have, this side s12, and bending moment you will have m12, and this side you will have s22, and you will have m22. So there's a, now opposite of the this force and this moment are going to act at node number 2. So here we will have this s12, and now the moment would be m12. So this is a free body diagram of node number 2. Now for node 2, if we look at the equilibrium equation, so for node 2, if you look at sum of all the forces along y direction equal to 0, so if you look at the force we have is, this is along plus y direction, so s12 minus s21 is in the negative direction, plus this externally applied load P, this is equal to 0. So you could see that s21 minus s12, that means you take these two terms to the other one side, so you can write that is equal to P. And since for the given problem P0, so if there was no Q was 0, small q was 0, only concentrated force P was applied at the say node number 2, then you will have S21 minus S12 equal to P. In this case, P is actually equal to 0, and P is the externally applied load along plus y direction at node number 2, which is 0. So this is one condition you get. And then if you take similarly the moment about z axis is equal to 0 passing through node number 2 itself, so that will give you the moments are this is the moment about positive z axis, so we will have m12. This is the moment about negative z axis, so minus m21, and then plus m this moment, no this one. So this is equal to 0, and if you take these two to the one side, so you can write m21 minus m2 is equal to m, and for the given problem this m is actually equal to 0, so we get m21 minus m12 equal to 0. So finally, so we got here S21 minus S12 equal to 0, and M21 minus M12 equal to 0. That is what we have now over here. So that is, this is equal to 0, this is also equal to 0. So now once we know these, so if you count the number of unknowns, so the unknowns are V2, theta 2, and then S11, M11, S22, and M22. Because now corresponding to these V and theta, they are 0, so these would be unknown. So the unknowns are 6, V2 theta 2, S11, M11, S22, and M22. So there are 6 unknowns and 6 equations, and we can solve these 6 equations and 6 for 6 unknowns. The step would be first to solve the equation 3 and 4 for V2 and theta 2, and then from first equation you can get S11, from second you can get M11, from the fifth you can get S22, and from sixth you can get M22. So this is how the whole solution procedure will follow. So I have already explained you that P and M here are externally applied, so they are 0 for this problem what we are considering, externally applied. Now there could be situation that no, there is a distributed load also, there is a concentrated force also. So then P will be considered, Q will be considered, or only Q is 0, P is non-zero, or maybe P and small q are 0 but only M is there. So all those possibilities can be there. So P and M are externally applied force and moments at global node 2. So the solution as I already said. Now how you will proceed? So you go to the first, as I said, you take equation third and fourth. So 1 3 and 1 4. So now if you look at those third and fourth equation over here, so this row will give you third equation, this row will give you the fourth equation. So this into V1 which is 0 plus this into theta 1 which is 0. So you will, and then similarly if you take this into V3 which is equal to 0 and this into theta 3 equal to 0. So only we will have the terms corresponding to V2 and theta 2. So this equation will give you EI by L cube is common. 12 plus 12 we get 24, minus 6L plus 6L is 0. So these are 0 0, and this is 4L square plus 4L square, we get 8L square into V2 theta 2. And the right hand side we have also just this as QL, and the other term was 0, and the external internal force we already have got that as 0. So if you solve this equation, it is straightforward in this case. So V2 comes out as no QL power 4 upon 24 EI, and of course theta 2 will be 0 over here. Obviously because of the symmetry you expect the deflection or slope at center is equal to 0. So node 2 is at center, so obviously the slope has to be 0 there, and that is what this finite element solution is giving you. And this is small l, I have already said that it is equal to basically capital L by 2. So if you write in terms of capital L, you would get QL power 4 upon 384 EI. So you can compare this result with the exact solution from any strength of materials book. So now this is what you get as V2 and theta 2. And now if you want to calculate reactions, so if you want to calculate reactions, so now if you take the equation number 1, so equation number 1 is, from that we are going to get M11, S11. And now for that equation of this element into V1, so V1 is 0, this into theta 1 is 0, then we will have minus 12 into V2, which is non-zero, and then 6L into theta 2, which is 0, and these terms are anyway 0. So if you look at the first equation, so you will have, of course, this no EI by small l cube is common, and then you get minus 12 into V2, and the right side you have no the QL by 2 minus S11. so now if you do the calculation, so you can say that S11 would be equal to QL by 2 and plus 12 BI by L cube into V2, and if you put the value, so we'll get QL by 2 plus 12 BI by L cube, and V2 is QL power 4 upon 24 EI. So now if you do the the simplification, you will get this as QL. So now if you took the similarly, if you take equation 1 2, the second equation, so you will get similar logic the way I have explained, EI by L cube, and you will get minus 6L into V2 is equal to, you have this QL square by 12 minus M11. So if you simplify, put the value of V2 whatever we have got and simplify, so you will get, you can see that M11 would come out as QL square by 3. Now the simplification I leave it to you. The way we did over here, same thing you have to do here also. Then from the fifth equation you will get basically S22, and from the sixth equation we will get M22. So now if I take equation number 1 5, so now the fifth equation if you take, so the fifth equation means this into V1 is already 0, this into V2 is already 0. Then we will have minus 12 into V2 plus 6L into theta 2. And this into V3 which is 0, so minus 6L into theta 3, that is also 0. Theta 2 is also, so as a solution it has come out to be 0. So the equation 5 then will give you EI by L cube is there anyway outside. And then we will have minus 12 into V2 is equal to QL by 2 plus you will have S22. So now if you do the calculation same way, put the value of V2 whatever you have got and then get the S22, so you will get this as minus QL. And then lastly from equation 1 6, now if you look at that is going to give you EI by LQ into 6L. So now if you see this fixed, the beam fixed at both the ends, it is statically indeterminate. So for finite element it doesn't matter whether it is statically determinate or indeterminate, you solve the problem exactly in a similar manner. So you are able to get basically the deflection and the reactions exactly in a same manner. So sixth equation gives you EI by LQ into 6L V2 is equal to the sixth equation, right hand side we have QL minus QL square by 12 plus M22. So from this you will get no M22 is equal to, now again you solve for this, so you put the value of V2 here and solve for M22 and simplify, you will get that as basically QL square by 3 again. So this is what comes out as the reaction solution. So now if you look at the free body diagram of the beam as a whole with no reaction, so if you want to draw, I am explaining you basically all these steps, although in some solutions you may not have to do this. So now if I look at the whole beam of length 2L, 2 into small l, so this is the externally applied load Q, and let us say this is some point A, and for the first element this was x coordinate direction and this was y direction. The length of the element is the beam is 2 into small l, and see we have got now if you look at the left side we have S11. So if you look at here I have already shown S11 is in the downward direction, and this has come out as positive, and M11 is an the moment like this acting on the left side. That's the force acting on the element, so therefore the beam, so S11 is in the downward direction and is actually equal to QL. So this side we will have this force Q into L, and then we have a moment which is QL square by 3. And then right hand side, if you look at, so that's the second element. I have, since I have already drawn the diagram over here, so as per our sign convention, S22 is in the upward direction and M22 is like this. So if you see, S22 has come out as negative. Now the S22, if you look at, S22 is minus QL, so that means it would be actually in the downward direction. So this will be QL, and of course M22 is QL square by 3, so that is in this direction. So QL square by 3. So this is the free body diagram of the whole thing. Now again, if you want to check the whether the equilibrium of the whole beam is satisfied or not, so you check no sigma Fy equal to, now you calculate this. So in the positive y direction, this force per unit length is small q and the total length is 2l. So this will become 2ql, and then these reactions are in the downward direction. So the reactions at the left and right are in the downward direction. So minus ql, and you see this is equal to 0. So the equilibrium equation is satisfied. Sum of forces along y direction for the entire beam including the reaction forces is equal to 0, so that is satisfied. So same if I take the moment about z axis passing through point A, so one is this moment is a no, because this is your x, this is your y, z is coming out of the screen. So this is the moment about positive z axis. So we have this ql square by 3, and then this is about negative z axis, so we will have minus ql square by 3. This is about positive z axis, so plus. This is about negative z axis, so it is negative, because no x axis is what z axis is coming out of the screen. So if you use the right hand screw rule, this is about the negative z axis. So this is minus ql square by 3, and then we will have no moment due to this, that is QL. So this is going to give you moment about basically no, the negative z axis, this QL, no, this reaction force, this is QL. So minus QL into the distance from point A is 2L, and then you have the moment of no, this distributed force Q. So that would produce moment about positive x-axis. So the total load is Q into 2L, because force into length and 2L. And then no, this because a uniformly distributed load, no, its resultant will be acting at the center, so at a distance L from A, so into L. And you see again this is also equal to 0, so this equation is also satisfied. So equilibrium of the beam as a whole is actually satisfied. So this you will always see. We can use any number of elements. So we know the global equations of equilibrium will be satisfied. So once we have done this, so then next is now we look at the now post processing. So post processing means the calculation of deflection, slope, curvature, stress, strain within each element. So let me look at that now. So next is post processing. I'm giving no, spending a lot of time so that no, you understand all the steps, because subsequently no, I will go faster. I will not be doing most of these calculations, because I will presume that you understand now, so you would be able to do. So, but initially, of course, I'm spending a lot of time in doing each and everything. So now, if you look at the no, element number 1. So that's the post processing. The element 1 is defined between global nodes 1 and 2. So first the deflection, if you look at V as a function of x, so we know this in terms of interpolation functions h1, h2, h3 and h4, Hermite interpolation function, into the vector of elemental degrees of freedom. So the V1 is 0, theta 1 is 0, V2 is q L power 4 upon 24 EI, and then theta 2 is 0. So this is no, yeah, DE for the first element. So you would see that no, V of x will be equal to only H3 into this QL square upon 24 EI, and H3 is 3x square upon L square minus 2x cube upon L cube, and into this is QL power 4 upon 24 EI. So this is V. Now if you want to, so this is the deflection, as you know, any, and this equation you can use to find deflection, at any point within the first element. So if you look at the slope theta, which is basically dv by dx, so it is a derivative of basically these functions. So this will become c 6l by l square minus 6x square by l cube into ql power 4 upon 24 ei. So you can use this to find the slope at any point in between the element. Of course, the slope at the left of the element is 0, slope at the right end of this element is 0 because theta 2 is 0, but in between the slope would be non-zero. So if you want to calculate that, you can use this equation. Say at center of the first element you put capital X is equal to small l by 2 and get v or theta at the center of the first element. So similarly, if you want to calculate the curvature, curvature is usually been denoted by rho 1 upon rho. So 1 upon rho, that is curvature. So curvature is 1 upon rho equal to d2v by dx square. This is used in defining the strain. So again differentiate this equation, so we would get 6l by 6 by l square minus 12x by l cube into ql power 4 upon 24 ei. So this is the curvature. The strain would be minus y into this d2b by dx square. We have already done that. So I am directly going to write the stress. So then stress, if you look at sigma xx, so sigma xx would be E times epsilon xx, and epsilon xx would be y times d2v by dx square. So minus, we have written this relationship earlier, that is stress is minus ey into d2v by dx square. So if you put this value, we will get this e here and this e will get cancelled out, and so we'll have minus y and then 6 by l square minus 12x by l cube into ql power 4 upon 24 I. So this is what will be the expression for sigma xx anywhere within the first element. So now, you can calculate the variation of stress along height of the beam, that is as a function of y, and it's also a function of x. So suppose you want to calculate the stress at the top leftmost point of the beam. So you can calculate sigma xx at x equal to 0 and y equal to either top or bottom. So let me put y equal to plus or minus h by 2. So plus h by 2 would be the top of the beam and minus h by 2 would be bottom of the beam. So this is equal to, because we have here minus into y, so when we put y equal to plus minus h by 2, we will get minus plus, and then we will have no, see this e have already cancelled out, so no, this e will not be there. So I have cancelled out with this e, so that e will not be there. So we'll have minus and plus, and then y is h by 2, and then d2v by dx square. So now you're putting, no, I'm sorry, here e is there, here it is not there. I'm sorry for that wrong deletion. So here you're putting in this expression y equal to plus or minus h by 2, so you get minus a plus h by 2, and then you're putting capital X equal to 0, so you will have into 6 by l square, and then you will have q l power 4 upon 24 I. So if you simplify this, finally you get minus plus qh l square upon 8I. So depending on the cross section, let's say the beam is of let's say a rectangular cross section of height small h and width b. So then this small I would be bh cube by 12, and you put that and then you get the stress, and that stress you will use for the purpose of designing. Of course, you'll have to find out where is the maximum stress. This I'm just giving you at two locations. One is just at the left of the element, at right where the beam is fixed, and the other at the center of the element. So say x is equal to small l, and y is again plus or minus h by 2. So this again you are going to put in this formula. So y is plus or minus h by 2, so we'll get minus plus h by 2, and then you are going to calculate this quantity, capital X is equal to L, that you are taking the right of the same element. So if you put no, capital X is equal to small l, so we will get minus 6 by l square. So we will have minus 6 by l square, and then we have this QL power 4 upon 24I. So now if you simplify this, you will get actually plus or minus QH no, L square upon 8I. So you see the sign of the stresses are actually opposite. So what I mean to say now that when you take the first element, so this is element number one, this is x, and of course in the element the load is there whatever. So if you are taking the here the sigma xx on the top surface, if you look at it is minus. The minus sign is for plus h by 2. So the stress here is compressive and here it is tensile. Now when you are looking at the center, it is plus minus h by 2. So the beam is under tension here and beam would be under compression here. So the sign is changing, as you see over here. So this is compression, here it is under tension, here it is tension, and here it is under compression. So basically, the reason for that is no, because if you look at this kind of a load, so right at this support, if you look at the bending moment is going to be because of this, and this is a negative moment. This bending moment is such that it will compress the beam over here and it will stress the fibers of the beam over here. But at the center, if you look at the bending moment is going to be predominant, is going to be dominated by bending moment due to this externally applied load, and here the bending moment is going to be of opposite sign. So therefore here it would be tension and here it would be no compression, like this. So that's the kind of stresses you are getting in the beam. So this is as far as the first element is concerned. Now let's go to element 2. So when you go to element number 2, so you have this is the element, the local coordinate is this x, and this is the y axis, and this is the local node number 1, global node 2, local node number 2, global node number 3. And now for this, if you want to calculate the deflection at any point, so v of x is the same, interpolation functions are same, h1 h2 h3 and h4, and then the degrees of freedom are now for this node and then this node. So v2 is that is q l power 4 upon 24 ei, theta 2 is 0, then v3 is 0, theta 3 is 0. So this is what you will have for the second node. So now it is in terms of h1. So you will see h1 is obviously 1 minus 3x square by l square plus 2x cube by l cube into q into we have ql power 4 upon 24 ei. So this is v at any point within the first element. So same way now if you want to calculate the slope theta, so that would be dv by dx, and that would be basically minus 6x by l square plus 6x square by l cube into ql power 4 upon 24 ei. So this is theta. Same way, know the curvature. So you know that all these things are similar to the first element. So d2v by dx square. So this is going to be minus 6 by l square plus 12x by l cube into ql power 4 upon 24 ei. Then if you look at the stress, so stress sigma xx, normal stress along x direction is E times epsilon xx, and this is equal to minus E into y into d2v by dx square, and if you put the values, so finally minus y into minus 6 by l square plus 12x by l cube into ql power 4 upon 24 I. So this is what you will get. Again, now you can calculate the stresses at top and bottom, left of the element, right of the element. So if we calculate sigma xx at x equal to 0, so now when you say x equal to 0, now it is actually this point. No, that is the actually center of the whole beam, because the first node is starting node, or the left node of the second element is the center of the beam, because we have discretized the whole beam into two elements. So sigma x equal to at x equal to 0, and again either top or bottom, so y equal to plus or minus h by 2. Y coordinate for the top surface is plus h by 2, and for the bottom surface, it is minus h by 2. So this would be equal to, now if you put the values again, because one minus sign is already there, so we get minus plus and then h by 2. And now in this expression, if you put capital X equal to 0, we get here minus 6 by L square into QL power 4 upon 24 I. So this will become plus or minus QHL square upon 8I. Now, so this result is same as what we have got over here. If you see, so it is basically same as this. So for this case, it turns out like this. In general, it will not always, the stress will not come out to be continuous across the elements. It's only this element is a C1 continuous, because V and dV by dx are continuous along the elements. But because of symmetry, we have discretized the beam into only two elements, and therefore, this stress at the end of say, first element is same as stress at the start of the second element. But that's no, only for this case. In general, it doesn't happen. There would be some discontinuity, and the discontinuity will be reduced when you increase the number of elements. So sigma xx at now x equal to L, and again y equal to plus or minus h by 2 would be equal to, so same way you have minus or plus h by 2 minus y will be this, and then now you put capital X is equal to L, so you will get 6 by L square and then QL power 4 upon 24 I. So if you simplify this, will be minus or plus QHL square upon 8I. So this is the stress. So this is the right side. It is actually identical to what we have got no, on the basically left hand side of the beam. So this stress is exactly same, because they at that point the bending moment is going to be same, so therefore same stress, that is what you are getting over there. So this is how the total calculations you will do. So you discretize the beam into a certain number of elements, assemble, impose the boundary condition, solve for the degrees of freedom, and then do the post processing, get the displacement, slope, the strain, stress at any point within each element. And then of course for the design purpose, you will use these stresses and make sure that the stresses are within the allowable limit of the material of the beam or the stiffener or ring in case of submarine or a ship. So now, as I already said, you can try solving different problems using the same assembled stiffness matrix. So I'm not going to do anything more on this, but you can have both in simply supported. You can solve the problem. Simply supported means then V1 and V3 would be 0, but theta 1 and theta 3 will be non-zero, but then the corresponding moments, no M11 and no M22 would be 0, and like that you can have any other the combinations of boundary conditions. So now let me also talk about, suppose the same problem you can solve using now one element also, although the solution will not be accurate. You'll have to do the convergence study, means you have to keep on increasing the number of elements and check the results, and when the two mesh give you the same result, and that is where you stop and you say that now I have a mesh which is converged. So but now if you want to just want to solve using minimum number of elements, so suppose you have a simply supported beam and you want to solve using finite element. So no not through the analytical approaches which you would have learned earlier. So I'm just telling you that different problems how you can solve. So this is a simply supported beam, so that's on a roller support, and the load is same. There can be a concentrated force or a distributed force. So I'm taking right now distributed force. The flexural rigidity is EI, and length of the beam is L. So earlier for the fixed beam, I had said that single element solution is will give you V everywhere equal to 0, so it will give you a trivial solution. But in this case, because the slopes are allowed at left and right nodes, so even the V, suppose you discretize this using only one element, that is global node number 1, global node number 2, and the element number as 1. Even one element solution will give you a non-zero V. Why? Because now the boundary conditions, if you look at V1 is 0, V2 is 0, but theta 1 is an unknown, theta 2 is an unknown. So when you say V1 and V2 equal to 0, So then S11 and S21 they would be non-zero, but M11 and M21 would be zero. No, when you look at no the single element solution, so you should be able to do the whole problem. So this I am giving as a homework problem. Solve using one element. Solve using one element. So this is a homework problem. You should do everything what I just did for the fixed beam using two elements. So now let me take another example. Sometimes because you want to the beam is resting on some supporting structure or a stiffener or say a pipe support. Suppose for example there would be a lot of pipelines running in the ship or a submarine, so those pipelines are supported on a stiffener, and stiffener in turn is supported on the body of the submarine or a ship. So that is kind of a flexible support or elastic support. So if you want to model that, I am taking a simpler example for modeling a elastic support or a flexible support. So that is cantilever beam on a spring support. So let us take the cantilever beam with spring support. So again I am going to solve this problem using only one element. So that is I am saying no some pipe support, a lot of pipelines. If you see in the submarine or ship, you would have seen there are pipelines, and pipelines are supported on some anchors, and those anchors we are treating as a cantilever beam. But resting on a kind of a support on the other side. So this one side of the beam is fixed. We are of course making some simplification by idealizing it like this. It may not be really exactly in a similar manner. So this is we want to discretize this using only one element. So the global nodes and local nodes are same, 1 and 2. The element number is 1, and the flexural rigidity is EI, and the load is loads can be actually concentrated or distributed. They need to be handled the way we have already talked about earlier. So this we want to solve using one element. Why one element? Although the left side v1 and theta 1 they are going to be 0, but the right side we will have some non-zero v2 and theta 2. So this will give you even one element will give you a non-zero solution. That may not be accurate solution. To get the accurate solution, you might have to use say 2 or 4 elements. That will give you accurate solution. But to demonstrate the steps, I am just using one element. So just I am showing the solution using one element. So solve using one element. So because it's one element, so if you look at the the assembled system is also going to be same as what is the element level governing equation. So 12 the stiffness matrix is going to be same minus 12 6L. We are assuming that EI is constant along length of the element 6L 4L square minus 6L 2L square, and then minus 12 6L 12 minus 6L, and then you have 6L 2L square minus 6L and 4L square. So because it's only one element, so the assembled system and the element level governing equation is same. V1 v theta 1 v2 and theta 2 is equal to, I have removed the e because now this is the global system, and this is QL by 2 QL square by 12 QL by 2 and minus QL square by 12. So this is there. And then if you look at the internal forces are minus S11 minus M11 and S21 and M21. So this is the assembled system now for a single element discretization. Now if you look at the boundary condition, if you look at now the boundary conditions, so I know for this, so the left end of the beam is fixed. So fixed means we will have the one set of boundary condition is that v1 equal to 0 and theta 1 would be equal to 0. And the second set we will get from the free body diagram of node 2. So if I draw the FBD of node 2, so if I draw the free body diagram of node 2, I am just only drawing the node 2 here. So this is node 2. Right side there are no forces. but the left side there are going to be force reactions from the element. So we will have S21 because S21 on the element is in the upward direction, so on the node it is in the opposite direction. Similarly we will have this M21 in the opposite direction on the element. Additionally, now additionally if you look at, because now this beam is supported on a elastic foundation, so what I am going to do is going to put a spring over here. So now additionally what I am doing is, because this is a spring support, so I am putting a spring over here and this end of the spring is fixed. Of course now this length is L and this is node 2 and the spring stiffness is, let us say, K. So if now V2 is the deflection at node 2, then the spring force would be K into V2 in the downward direction. So in the beam at node 2 there is going to be force which would be K into V2. V2 is the extension of the spring, into K will give you the spring force, and V2 is positive in the upward direction. So spring force would be acting on the node in the downward direction, and the spring force would be in the upward direction KV2, but on the node 2 the force would be in the downward direction. So this would be KV2. This is the spring force. So one is, if you write the moment equation, you will directly get M21 equal to 0. So that means this term is already 0. But if you write the force balance, so minus you have S21 minus KV2 equal to 0. Sum of forces along y direction equal to 0. So this will give you S21 is equal to minus K into V2. So yeah, so that's now the S21 is non-zero, which is minus K into V2. V2 of course is an unknown. So now the as far as the solution is concerned, so we already have V1 and theta 1 0. So we take the third and fourth equations and solve for V2 and theta 2. So we look at the third and fourth equations. So if you look at the equation 2 3, so let me number this equation as 2. So then you can say, if you take equations 2 2 and 2 4, so you have this EI by L cube. We are taking the third row and fourth row. Since B1 and theta 1 are 0, so they do not contribute. So we'll have 12 minus 6L minus 6L and 4L square. And this side we have V2 and theta 2. So this is equal to, you have, see, you could have actually, you could also do, now in the last equation, now if you look at, now this S21 is equal to, the third equation, S21 is minus KV2, and this minus KV2 you shift it over here, so you make this term 0, and this side, no, you write add the K term here, because EI by L cube is taken outside, so you will write plus KL cube upon EI. So you can do right there before imposing the boundary condition, or you can do this way also. So you will have here QL by 2 and then minus QL square by 12. These are already there, and plus now we have this S21 which is minus KV2 and M21 which is 0. So this is what you have. And I just said, no, this term you can take towards the left hand side, and no, so first, now here is this equation, so V2 is going with this term, so if you take this to this side, you can write that as EI by L cube, and 12 you are taking this, and because EI by L cube is common, so now you write here KL cube upon EI. So this is what this term would be. This is minus 6L and 4L square, then V2 theta 2 is equal to QL by 2 and minus QL square by 12. So now you solve this equation for V2 and theta 2, and once you have done that, then you can solve for the S11 and M11, the reaction force and reaction moment at node 1. So the solution is same, only thing you have to solve the simultaneous equations here. Solve for V2 and theta 2, then solve for basically no equations 2 1 and 2 2 for S11 and M11. And once you have done this, you can do the post processing, get the slope at any point within the element, you can get the curvature, you can get the stress, so all those calculations you can do. So I think I want to stop over here. Now if you have any questions and doubts, you can ask. So yeah, I want to stop here. Now if you have any questions and doubts, now you can ask. So is anyone having any question, any doubt? Yes, please. And please make sure that no, if you don't understand any of the things, you should ask. Actually no, you people don't ask. I unmute you and ask you to stop me anywhere in between and ask questions and doubts. No, if you don't understand, only thing of course you'll have to study. No, you have to study the previous lecture and you have to be attentive in today's lecture. But yeah, no, these are very useful. No, when you go to the design and anything, you will use these, and of course you'll have to pass the exam. That's anyways there, with good grades. So for that also basic understanding is needed, and then only you would be able to do well in the exams. Of course, some discussion about the minor we will have in the next class, after the next class. Today I just want to stop here. So anyway, any questions and doubts, if they are there, you can please ask. Any questions, doubts? Okay, so if there are no questions, I'm stopping. Thank you all for your attention. Thank you very much.